Thank you. Gotta record this thing. Okay. We are recording, yes. Here's the schedule for the next few weeks. We're doing Overflow, then a couple web-oriented attacks. And then we get to that, there's a second exam, and shortly after that, there is the last data drop. Okay, but today we're talking about Stack Overflow and some programming security flaws. Okay, I want to make the certificate students feel at ease, that you do not have to be a programmer. We are going to talk a little bit about programming flaws. You cannot talk about computer security without mentioning that there are a number of things that a programmer can do or not do that will greatly improve program security. And so we're going to talk about some of those today. Although I understand that several of you are not programmers, it's okay, we're going to work around that. All right, the first big item for keeping your program secure is making sure that the input that the user types in is correct and doesn't cause any sort of problems. You're going to make sure that it's the correct type and the numbers are within range. Of course, it's easy for people to make mistakes, enter something incorrect. Your program should catch that quickly. It's much easier to catch an input error early so that you can check it, tell the user they made a mistake, ask them to re-enter the value. Because later on, if you have bad data, it may cause a problem in your program. It may be very difficult to figure out why did the program break way over here when the error was made way over there. An example, let's say we're going to read in phone numbers. Now, phone numbers have a particular format. Actually, they have multiple possible correct formats. If we want to check for international numbers, we want to check to see it starts with the country code. But for the simple US phone numbers, they're 10 numerical digits. They can be entered in many ways. You can just enter the digits. You can put parentheses around the area code, a dash after the 3-letter exchange number. There's multiple ones, but you can define a number of patterns and then check to see that the numbers that you read in meet one of those patterns. Another way to check to see if your input is correct is to have check digits. Frequently, when you have to enter a long numerical string, such as a credit card number or a book ISBN number, there's a check digit. This is the algorithm for the last digit on an ISBN. So when you get a book, they all have ISBN numbers. Now, they usually have 13-digit ISBN numbers, but they also have 10-digit ones. I have not updated my slide to give you the 13-digit algorithm. It's probably similar to this. They add all the digits from 1 through 9. So they add the first 9 digits together, divide it, and get the remainder mod 11. So divide it by 11 and get the remainder. That is the last digit. So the last digit is the sum of the first 9 digits divided by 11. The remainder is the last digit. So when you read in the input, you can perform that algorithm yourself. You can add up all the digits, divide it by 11, see what those, and you've got a 1 in 10 chance, actually a 1 in 11 chance that you got the correct one. Now, it is possible if it's mod 11 that the remainder is 10. In that case, they use X. So every now and again, you'll see an X at the end of an ISBN. That's because the sum of the digits, mod 11, is 10. So this is an easy way to check digits. It doesn't always tell you that you got a good one, but you have, I think, a 1 in 11 chance of sneaking through with a bad input. Another thing to watch out for sometimes is character codes. The input is usually in ASCII. There's multiple character codes. There's UTF-8, UTF-16, Unicode, ASCII. Unicode is used by Java and several other programming languages. ASCII is used by C++ sometimes. In ASCII, there's 8-bit or 1-byte character codes. And each pattern of bits represents a letter and a number and whatever else you want to. for instance, a decimal 65 is an A, or hexadecimal, that's 4-1. It's an A. So actually, I think that's 2-1 is an A. So there it is. And Unicode, of course, they're bigger. You shouldn't be confused by the value of the character and how it is represented on the screen. Fonts explain how the character should be displayed on the screen. There are all sorts of different fonts, and I have lots of fun with fonts when I make slides, make homework assignments, and send emails. You have all different fonts you can deal with, but for every font you have, the letter is still the same. So if you copy it from one font to another, the A will remain an A, which will remain an A. Numbers are almost always stored as integers, whole numbers. Now, we're not talking about floating point numbers or numbers that have a decimal point. I'm not going to talk about the decimal point value for doubles and floats. That's not necessary for this class. But it is interesting to know integers, because there are some exploits that evolve out of storing the numbers as binary. So generally, numbers are stored in a binary. If you're a programmer, an int or an integer is stored as a binary number. Now, computers tend to use base 2 or binary. Humans use decimal numbers because we have 10 digits. Long ago, in the dawn of time, when people started to count, that was how they counted on their fingers, and so we did base 10. I suppose if octopus had learned to count first, we'd be base 8, but we're base 10. And when you have base 10, each position is 10 times the position to the one on the right. So the rightmost digit goes from 0 to 9. The next digit represents 0 to 90, and then you have the 100th digit and the 1000th digit. So 3,148 is 3,100, 4 10s, and 8 1s. Binary numbers are similar, but we go by base 2 instead of base 10. If you just use your thumbs, it works the same. But basically, every digit is only 0 or 1, one of two values. And when you look at them in a binary number, the rightmost digit is the 1s, then we have the 2s, then the 4s, then the 8s. Each position is twice the position before, whereas in decimal it's 10 times, in binary it's just twice. So if we have 1 0 0 1 1, we have 1 16, 1 2, and 1 1. So you add 16, 2, and 1 together, and you get 19, which is correct. 1 0 0 1 1 in base 2 is 19 in decimal. Okay, that's a positive number. Positive numbers are easy. What do you do for negative numbers? Because in theory, half the numbers are negative. Well, there are multiple ways to keep track of negative numbers. There's 1's complement, 2's complement, sign magnitude. We're going to worry about 2's complement because almost every machine made uses 2's complement negative numbers. For integers, I might point out that floating point numbers are sign magnitude, but we're not going to worry about that. Okay, so here are all the possible bit patterns for a 3-bit number. You go from 0 0 0 0 0 1 counting up, and half of them are negative, half of them are positive. So if the leftmost bit of a 2's complement number is a 1, then the number is negative. So that's how you can tell. You can convert from a positive number to a negative number very simply. You just switch all the bits and add 1. So say we want to figure out what is the bit representation for a -3 in 4 bits. We're just going to do 4 bits because it's easier to show. Instead of showing 32 bits, we'll just show 4. So you start with the positive value. 0 0 1 1, there's a 1 in the 2's and 1 in the 1's, so 2 and 1 is 3. So this is a 3 in binary. Flip all the bits, meaning make all the 1s 0, all the 0s 1. So flip all the bits, you get 1 1 0 0. And then you add 1 to the results. So 1 plus 0 is 1, and then everything else goes the same. So it ends up being 1 1 0 1. and that is a -3 in a 4-bit 2's complement number. Another example here, what is 1010 in 4-bit 2's complement number? Okay, so we flip all the bits, so it becomes 0101, add 1 to 1 becomes 2, or 0 carry the 1, 1 and the 0 is 1, so it's 1100. That is a 6 in binary, so it was a negative number, so we make it a -6. So 1010 is -6 in binary numbers, 2 complement. Any questions about that? Even our non-programming certificate students should be able to figure that out. Any questions? Okay, right. If nobody has any questions, then we will move on to our first poll question for today. Yes. I note that just looking at the poll question online, it does not have the 1001. Okay, 1001 is the value we're trying to convert. So folks here in the small live studio audience, okay. Okay. Everybody got it figured out? You want to hold your card up? Half the class doesn't have the card up. Let's see if you have it. Oh, wrong button. Okay. Oh, we got it. We've increased our participation by 100%. Okay. I think we have. Oh, well, I'm not sure. Okay. The popular answer is a -5. Let's see if we can figure out this. Oh, I should have shown this, but okay, 1001. Let's flip all the bits and it's 110. Now you add 1 to 110, it becomes 111. That's a 7. 111 is binary, so there's a 4, there's a 2, there's a 1, add them together, it's 7. So the answer is D, -7. Questions about that, because a whole bunch of you said -5. Did I fool you? Okay, well, that's -7. Important thing to remember is that the leftmost bit is the sign bit. Let's look at some more examples of negative numbers. When you do arithmetic with 2's complement numbers, you can add positive numbers and negative numbers the same way. Nothing special about a negative number. On the right here, we have a 7 and a 2, and we add them together. 1 and 0 is a 1. 1 and 1 is 0, carry the 1. Carried 1 and 1 is 0, carry the 1. And we get 101, which in fact is 9. That's correct. And here we have a positive number, and we're adding a negative number, which of course is the same thing as subtracting. And we end up 000, adding the numbers together. And at the end, we have a 1 and a 0 is a 1, a 0 and a 1 is a 1, a 1 and a 1 is a 2 or 0, carry the 1. Now we have 1, 1 and 1 is a 3, 1, carry the 1, 1 and 0 is 0, carry the 1. The carry out of the sign that is just ignored. When it carries out of the sign position, we just throw it out, drop it into the bit bucket. So we end up with the number 01. It happens to be 98, which if you get out your calculator and you add 104 and -16, you do get 98. So, you get, well, okay, it should be 88. It works. My calculator doesn't work, but the number works. Trust me, that works. I realize now that the difference between 104 and 98 is 6, not 16, but Okay, the slide is wrong, but the concept is correct. Okay, moving on. Now, something important to note is that as you can carry in to the sign bit. So let's look at this. We're going to add 6 and 3. So 0 and 1 is a 1. 1 and 1 is 0, carry the 1. That 1 and 1 is 0, carry the 1. 0, 0, 0, and 1 is 1. So we have 1, 0, 0, 1, which we should have calculated earlier is -7. So you add 6 and 3 to positive numbers, and you end up with -7. That's not the way they taught you back in elementary school. So that can be an issue sometimes. If you exceed the maximum range of a number, it will usually overflow. Here's the range of simple programming numbers. Int, which is the most common integer, ranges from a -2 billion, 2.15 billion, down to -2.15 billion. So it's if you just remember, it's about 2.1 billion or so. Longs are really big. They are, of course, 64 bits. Shorts are 16 bits, and bytes are just 8 bits. So there it is. Knowing that numbers is not real important, although it is sometimes important to remember that an int has a maximum value of around 2 billion. Now, it is possible that a program might overflow. Let's look at this very simple program. Programming experience is not required. This is in Java, but it could be in other languages. The whole concept is we want to set this logical value OK to true if and only if cow plus 5 is less than 12. So cow is some value we read in. If you've suffered through my programming classes before, you know my habit of choosing animals as variable numbers. So if you see an animal, it's just an arbitrary variable number. Okay, so here we read the integer cow from the keyboard. That's what this is doing. So we read the number cow, and then we say, well, if cow plus 5 is less than 12, which is what we want to check, we'll set OK to true. Pretty simple. But let's think about this, the idea of overflow. What if the user entered a very large number, entered the maximum number that you can have for an integer? Since this may be an attacker who knows what they're doing, so they enter this very large number. And then the program, following the requirement of cow plus 5 is less than, it's going to add 5 to cow and then compare it to 12. Well, when you take that very large integer and you add 5, and here's that very large integer in binary, and there's 5, and you do the arithmetic, and you end up with this number, which is negative. So cow plus 5 turns out to be a very large negative number. So when it compares the large negative number to 12, it says, well, yes, the negative number is less than 12. That's true. So that, in fact, will cause a programming error. Cow plus 5 less than 12 is not going to always work right if the user enters an invalid value. It could cause a program error. Another way to do this would be to go cow is less than 7. A little bit of algebra that you should have learned from high school. You just subtract 5 on both sides and it becomes cow is less than 7. That works. So the programming rule is never do any arithmetic with a value before you check its range. Even putting that arithmetic in an if statement can cause the program to overflow. And it overflows silently. No error is generated. The program simply doesn't work correctly. If you add numbers together and they overflow to become a large negative number, you just get a large negative number as an answer. There is no error message involved. So you want to avoid that because it is possible for users to enter really big numbers and cause your programs to not work correctly. So again, check that numbers are in range before you do any arithmetic with them. And if it's possible the numbers might be bigger than the size of it, use a long. Of course, you can still exceed the size of a long. It's a bigger number. Often it's useful to read it as a long, convert it to an int, and see how it works. Some other guidelines I got from the OWASP website. OWASP is the Open Web Application Security Project. It's an excellent source of information about computer security, and I will probably reference it multiple times during this course. And if you ever have questions about computer security or a topic in this class, you can always go out to owasp.org and look it up. They have lots of information. OWASP gave these guidelines along with several others. But these are the ones I thought were the most important for checking, but make sure you're always using a common character set. In other words, don't be checking ASCII characters against Unicode characters. Sure, they're the same character set. And again, validate all the user input before you do any processing, before you do anything. Make sure that you check the user input as it's entered. It's much easier to recover from an error than just ask the user to type in a better value, because if you let it go, the program will probably generate an error far down the line where it's much harder to figure out what's going wrong. And of course, if there is some validation failure, if it doesn't look good, don't use it. Got to check the range, check the data length. That's often very simple. You read it in as a string and you see how long is the string. Is this too big? Then you've got a problem. And when you're checking characters, you should check to see that you have valid characters. This is often done when you're looking at a URL, a web link, or some other data that may have a number of different characters. Check to see that all the characters entered are on the list of good characters, as opposed to checking to see if it's on a list of bad characters. So it's much more secure to check, is this character in my list of good characters, than to see, did they enter what I think is a bad character? Turns out it's much more likely you missed something if you're looking for bad characters. If you're just checking for good characters, it's more likely you'll check correctly. Of course, one can argue about whether the good ones are the white ones and the bad ones are the black ones. That's a discussion that's been going on for many decades. And we won't talk about it here. Okay. This is, as you might see, a very old warning from CERT. I get these things all the time. Every day or two, I get a warning from the computer emergency response team telling me about what's the problem of the day. And there's almost always a problem of the day. This is an old one, but I pointed out because it mentions buffer overflow. I want to talk about buffer overflows. They're pretty common and they are a major threat. Even the more common ones, which emails look a little bit different format, still includes buffer overflows. Nowadays, they don't send one email for every error. They send an email and point you to a list of errors. The world has gotten busy. But buffer overflows are a very significant source. Whenever you get an error alert, you look at it, it says, usually you see a phrase that's something like, the most severe of these vulnerabilities allows a remote attacker to execute arbitrary code. You're almost always talking about a buffer overflow. That's a way that a user can put their program into your computer and run it on your computer. And there's not much worse you can do than run somebody else's program on your computer without your permission. Unfortunately, a lot of students don't know what buffer overflows are, but we're going to learn about it today. All right, mentioned historically, for those of us with gray beards, we remember back in 1988, when Robert Morris, who was an MIT grad student, generated the Morris worm. The Morris worm was particularly notable because it shut down the internet for about 2 days. It was the first big internet attack. Mr. Morris did not intend to shut down the internet. He was a grad student and he just wanted to show a proof of concept that this would work, that you could propagate values across the network. The worm, the program, worked on the Unix finger command. Finger is a command that allows you to see if somebody's running on another computer. You can finger the other computer and say, is Joe actively running now over there? And it'll say, yes, Joe's running and he's used this much time on his computer. And you can see what Joe's doing. But there turned out to be a stack buffer overflow vulnerability in the server part of the finger command. And Mr. Morris saw it, exploited it. The Morris worm copied itself onto your computer, and then it ran again. It was only supposed to go so far. An error in the program said that if it copied itself into your machine. It would still keep making copies. So it kind of took over. Might note that they caught him, and he was the first person to be penalized for breaking the law about malicious software. I don't remember which law it was. He got 3 years probation, 400 hours of community service, and a $10,000 fine, which, by the way, that was back in '88. It's equivalent back now to about $20,000. So it was a significant fine. Yes, question? He didn't really mean to take down the internet, so he says. It was an error in his code. The program was 99 lines long. It wasn't a big, sophisticated program, but there was a bug that made it propagate more than it was supposed to. It was supposed to go so far and stop. It didn't. It went so far, and then 14% of the time it kept on going. And so when you had a couple thousand copies out there, it just kept on running. You know, the Energizer bunny of worms just kept on going all over the place. It was interesting. I was a grad student myself at the time, and it was interesting that, hey, some grad student took down the internet. Wow.
I didn't see, contested. His intention wasn't to.
Well, they didn't send him to jail.
Yeah,
They gave him, 400 hours of community service, which is not, that's like 10 weeks of full-time work. I don't know how to, and $20,000 fine. I would notice a $20,000 fine. I prefer not to get a $20,000 fine. Thank you. As a grad student, he is now, by the way, a professor at MIT. So didn't hurt his career too much.
So if you were to go on the internet when that happened, would you just happen to get like an error message, or it would not open?
Oh, what happened when he ran it?
Yeah, I guess like
He didn't have to run it. It started itself.
Okay.
Yes, he copied it on your machine and started it on your machine. So it duplicated itself. We'll talk about self-duplicating programs and other fun things later on in the class. I think we have a whole lecture on malware, the whole zoo of viruses, worms, bugs, and all sorts of other creatures that can attack. So that's coming up, but this is notable because it was a buffer overflow attack, and we'll talk more about buffer overflows in the next few minutes, starting with this question. So let me start that. Okay. Hopefully you can see the program because I didn't copy it into the poll question. I understand that several of you are not programmers who've never written programs, but just look, I have highlighted the numbers of importance. The 4 and the 7 are particularly important. We have 4, meaning there are 4 info values. So the index goes from 0 to 3, and then we have a loop that goes from 0 to 7, or actually 0 to 6 to be exact. So what is the C++ program going to do? And we've got only about 20% participation online. Let's see if we can get a better participation here on our live studio audience. Okay. All right, ready? No, we're not ready. Okay, got one there. One there. You got to show it to me. Okay. Yeah. All right, got it. All right. Look at, okay, online, everybody got it? Okay. Online, okay. There were about a third of you said roughly a third said there would be a compiler error. That when you compiled it, the compiler would not, that is, when you first try to compile the program, it would say, nah, this isn't gonna work. A runtime buffer overflow error was 2/3 of you. And only one person online said it's going to corrupt the data, which is in fact the correct answer. This is a C++ program. C++ programs do not catch an array, out of range array reference. If it was Java or Python, yes, you get a runtime buffer overflow, but not, I might point out, if you're running it in C++. C++ doesn't care. If you know C++, lobotomy will get you to C. Remember, plus in C is the add one. It's the object-oriented version of C. So C was created in the early 70s, and then in the 80s, Bornstrom created C++ by adding object-oriented constructs to it. That's good. You're in 422? Oh, 620?
No, it's a microprocessor.
Well, what, you in 422 here? Why are you here?
Why am I here? This is for another degree program.
Okay, well, anyway, yes, if you're an undergrad student, I hope you know C++, because we're going to talk about that in a little bit. There's an assignment coming up. So Quake in your, okay. Don't worry, I'm not going to flunk you all. All right, basic overflow concept. Let's imagine we had this variable called root privilege, and we'll start off with false. In C or C++, by the way, particularly in C or C++, if a value is 0, it's false. If the value is non-zero, it's true. So there's one false value, and anything else besides 0 is true. So here we have a 8-character buffer to hold a name, and we're going to read C in a console input going into the name. That's going to, program will stop, ask the human being to enter something in, the human being enters something in, presses the return key, and it takes that value, it takes those characters and stores them into the variable name. So the user types in the word Smith, S-M-I-T-H, puts in the character name, no problem. But what if the name's Armstrong? Armstrong is 9 characters. With the first 8 there, and the 9th character goes in the byte after the character. Well, it may be that the root priv variable is located after that character array name. And so by putting the G in there, G, of course, is a non-zero value. Whatever binary number represents a G, which is unimportant, it's not a 0. So now root priv has become a positive number. And it is a true value. Okay, we're going to pause for a minute. Maybe. Let's I can so I'm going to stop sharing the screen. I'm going to share another screen. And hopefully everybody sees the command mode screen. This is Windows command mode. Okay. I have a program, easy overflow, which I'll execute. And it's going to ask me for a password. I happen to know that the correct password is G, capital letters. It's got to be G-O-O-D. If you enter the correct password, it says password correct. If you enter a wrong password, excuse me, let's type the program again. Easy over, type in the wrong password, and it says incorrect password. Okay, it's real simple. It reads it in, checks it. But this program is susceptible to buffer overflow. If I run the program and I type in something that's longer than 8 characters, oh, it wasn't supposed to do that. I thought I had taught it. Well, okay. When I run it in the debugger, it does the buffer overflow. And apparently the executable without the debugger has too many catches. We'll talk about why C++ caught that. Let's just one more try here. 1, 2, 3, 4, 5. No, it catches it every time. All right, it caught. It didn't do what I thought. I should have tested this, I suppose. I tested it in the debugger multiple times, and well, whenever you do it, you should never do live demonstrations. Let me tell you, they never work right. Okay, I should learn. I knew that. All right. Again, hopefully those of you online can see the basic buffer overflow, and we will move on to Stack Overflow. Stack Overflow is similar to a buffer overflow. Again, you go past the end of an array into the data that is beyond that. It turns out, though, that data values, particularly what we call automatic variables or local variables to a method, are stored on the program stack. The program stack keeps the local variables, save areas, and it keeps the return address of where the program goes back to. When you call a function or a method, it has to keep track of where was it called, because you might call it multiple places in the program. It has to know where to return to. So that information is kept on the stack. It is possible to go past the end of your array and overwrite the return address. In clever data, you can put values in the return address that cause problems. Now, there's another Stack Overflow. If your stack gets too big, typically like runaway recursion, you're just allocating great big values in the stack, and call a method, calls a method, calls a method, and each one has great big values. You can run out of stack space. That's a different problem. We're not going to talk about that. Here is basically way that memory is organized, at least in your Intel processor and most other processors. We've got your program instructions and your global data down here at low addresses. Of course, this is all low addresses for your program, not low addresses for the machine. Typically, each one of these segments is located someplace in your program. Then you have the stack and the heap. Stack and the heap both grow dynamically. The stack grows from given address down. In other words, it starts at some large address, and everything that's put on the stack, when you push something new in the stack, it puts it at a lower address. And you keep doing this, and hopefully you never run into the global data. If you do, either terrible things happen or your program gets an error. Terrible things can be much worse than your program getting an error. I mean, you've corrupted data values in your program, and it may be much, much later that you detect this in weird ways. Then there's also the heap. The heap is where new values, when you go out in an object-oriented program and you say new, I want to create a new object, or you go malloc and I want to grab some memory, it takes it from the heap, and the heap gets bigger and bigger, growing to higher and higher addresses as it needs more space for the dynamically created objects in your program. So those are on the heap. So we've got the stack and the heap. Both of them grow dynamically as the program executes. And you put things in the stack and pop things off the stack, it's here. Okay. Byte ordering. I might point out, if you look at memory values, and I've decided we're not going to do that today, but if you do look at them, and it's interesting to note that the Intel processor, the AMD processor, and I'm not sure about the ARM processor, are little endian machines. Little endian machines, as opposed to big endian machines, store the 4 bytes of an integer in reverse order. So let's look at this number here. We have 258, which is a little bigger than will fit in 1 byte. The 01 is in 1 byte, and the 10 is in another byte. If you had just a regular big endian, it's normal binary, just like you think it would be. And the number has a 0 in the end, and the 0 is there, and the 0, 1, there's the 1. If it was a little endian, then they reverse the order of the byte. They do not reverse the bits in a byte, just the order of the byte. So the least significant byte comes at the lowest address, or it's the first byte is the least, then that. So you can see they've reversed the order of the bytes. It's weird. That's the way it's done. Heaven, well, I don't know why they do that. It's long ago, far away, when they had the Intel 8080. Remember how you do arithmetic from elementary school? you start by adding the rightmost digit and the other rightmost digit, add them together, you get them. So if your program goes out and picks up the rightmost digit first, you can start adding before you get the second digit. And so they put the numbers in reverse order so the machine can start grabbing the rightmost digit and they can start doing the arithmetic before they even got the second digit, trying to make it run faster. Remember when machines had a 4 megahertz clock, not gigahertz, 4 megahertz, like 1,000th of a gigahertz. They were slow and you wanted to make it faster in any way you could. So that's why they did that. It historically, though, it was a mistake. Okay. So let's look at this simple program where we have a function that takes a pointer to a variable and an integer, and it has a local variable. Okay, what's happening here? Well, I'm going to call it with trout. This trout is a pointer and bass is an integer. So the first thing they do is they push the value of bass rightmost first. So they're going to push them because remember stacks, it's first in, last out. So bass being the second value, they push it in first. So they put the value of bass. Now, trout was an address. So they put the address, you remember, this is a address. So put the address of the variable there. And then we call the function. Calling the function pushes the return address on the stack. That is, the address where the program did the call statement is stored in the stack, and the program jumps to the method to start executing. When it starts executing, it puts the frame pointer there. We'll talk about frame pointers in a minute. They link all these areas together. So if your program gets an error, it can print the history of where this method was called by this method was called by this method. How does it know that? It changed those frame pointers back. All the frame pointers point back. This was called from this was called, and that's how they undo it. Yeah, the frame pointers. If you don't think about debugging, then the frame pointers don't do a lot, but that's the big purpose, and they really save you when you're debugging. And then there's the local variables are on the stack. So that's what we see on the stack. Now, here we have a bunch of important values, including the return address and a user variable here. If you write beyond 4, in other words, there's 4 bytes to cow, 0, 1, 2, 3. You write too many, then it writes it into the next value. If you write values 8 through 11, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 are the return address. If you can convince the program to read in data that is significantly longer than expected, if expected a value less than 4 characters, and you gave it at least 12 characters, you will overwrite the return address. And if you're really evil, you overwrite the return address, you can put binary values there that make sense in that program and cause it to go someplace else when it returns. So instead of returning back to where it was supposed to, the program continues to run. When it gets done and it returns back to the calling program, it doesn't go back to the calling program. You have changed the stack and you put it someplace else. If you are, okay, I think I just said this. So, okay, the whole idea is you're going past this value in the frame pointer. It's usually, by the way, good to try to overwrite the frame pointer of the reasonable value, otherwise you may get errors. And then overwrite the return address so it goes back to it. You can even get worse than that. Beyond changing the return address, you can then start loading binary values in machine language, load a program into that. So if you have a very long input, user expected a very short one, but instead you've redirected it to get data from a file that you've carefully constructed that contains an inappropriate return address and machine language, can cause it to jump into that machine language. Then it will execute that program that you loaded off the data, and that causes it to run a program. Once the attacker is running their program on your computer, you've been had. There's little you can do to save yourself. Okay, so quick poll question just to see if you're awake. All right. Okay, let's find out what people thought the answer was. Gotcha. Gotcha. Okay. All right. Everybody done? We only got 12. It's not 60%. It's not a very good return rate. Oh, okay. Well, 13. So anybody else? We've got almost an even division. A couple more people could have voted for low binary machine learning. All these are possible. I might point out that a Stack Overflow can do all of these. You can change return address to call some other function. That's certainly possible. You can crash the program by putting junk in the return address, and it will crash when it goes to return. Alter data, just like any other buffer overflow, you can alter data values. But I think, in my personal opinion, loading binary machine language is the most evil thing, because that allows the attacker to run an arbitrary program on your machine. And they can do most anything. Typically, these programs you're loading will then go out and get a larger program, download that, and now you're really in trouble. Okay, so I would say loading binary machine language is the most evil. Okay. Just a reminder, week from next week on Wednesday. Next week on Wednesday, graduate students have a paper that's due. I think everybody's got a topic now. I sent topics to those few people who did not choose topics. Paper is going to be 3 to 5 pages in length, not counting references and title page, single space, space and a half, 1-inch margins, you know, and some format that I can read. Thank you very much. It must give your personal opinion on the topic. Each topic was a statement that you either have to support or refute. This isn't a book report. This is telling me what you think about that. But I don't want just your opinion. You have to back it up by facts from at least 4 reliable references. Now, this is the internet. You can find anything on the internet. Just because it's on the internet doesn't mean it's true. Let's try to find reliable sources. If you're looking for reliable sources, scholar.google.com is good. If you go to Wikipedia, look at Wikipedia, and then look at the references. Wikipedia always has a bunch of references down at the bottom. Follow those references. Those are good references. Some people will tell you Wikipedia is no good because anybody can change it. I'll challenge you. Somebody thinks you can change something, we'll do a contest. You can find something and change it. And we'll start, tell me what you want to change. We'll look at the website, we'll see what it looks like, and you can change something to be wrong and tell me if how it is. It's not as easy as it looks. Look, I remind you, plagiarism is a sin. You cannot plagiarize, you cannot copy somebody's other's idea without telling who you got it from. It's very easy to do it correctly. All you do is whenever you reference something that somebody else said, put a reference there. Typically, most students use square brackets and a number, and then in their references, the references are numbered, 1 through whatever, and they say this is reference 4. There are other formats you can use. I don't care what format you use. Anything you do is fine as long as I can figure it out. If you're actually doing direct quotes, put it in quotes and cite it. If you're just including it as kind of this is what this person said, not necessarily a direct quote, you can just put it in the text of your paper and put a reference so we know where it came from. Don't make me think that you thought of that idea when in fact you didn't. Okay, so we've talked about the fact that buffer overflows are bad. How do we get around it? What do we do to avoid those problems? Well, one thing you can do, here's a list of things you can do. Better software engineering. I'm gonna go over each one of these in some detail. So let's go. Programming errors. Again, programming errors are often caused by poor programming. Or buffer overflows could be avoided if the user had written the program better. We'll talk about libraries in a minute. Excuse me. Good software engineering, code reviews are always wise. If you're writing production code, have somebody else look at it. It should be a formal method where somebody looks at your program to decide whether it's likely to work correctly or not. You look at their program, they look at yours, and then that way people will notice, oh, you forgot that this could happen here. Of course, test it. There's a technique called fuzzing. Fuzzing, where you just throw random data at it. Random data isn't as good as carefully crafted bad data. Look for data that's too long, data that's going to try to break it. Frequent vulnerabilities. Use of buffers without bound checking. Off by one errors. If an error has a name, you know it's a problem. We'll talk about that in just a second. Unsafe library. Watch out when you're taking programs that were written for ASCII and using for Unicode. Remember, Unicode's twice as big. You got to increment by 2 to get the next character. There's a whole bunch of other ones out there. Off by one errors are very common. Off by one, almost all the programming languages, except for Fortran that I know of, and COBOL, everything else starts arrays at 0 and goes up to 1 less than the size of the array. So in this example here, we have my string is an array of 10 characters. They can be indexed 0 through 9. You cannot put a index 9 in there. In fact, in C terminates the character with a null. How long does C know that, how does C know how long a character string is? It goes through until it finds a null character, a character with a binary value of 0. You have to leave space. So in fact, if you have this indexed to 10, you can only put 9 characters in it because it needs space for that null character. If you think you can put 10 characters in there, that null character will be stored in the byte after my string, which may cause a problem. Oh, will definitely cause a problem with that one. Unsafe libraries. There's a bunch of C libraries, old C libraries that do not consider the length of the buffer where things are going to be copied. They just assumed way back in the early 70s that everybody would write perfect programs and nobody would make mistakes. So why would we need to worry about this? If you're going to copy something into an area that's a given length, then you would never copy more. But also there were issues with pointers. If you have a chunk of memory and you're pointing to it, the compiler may not have any way to know how big that area of memory is. So there are several problems, and they have been inherited by C++ because C++ is just an object-oriented version of C. Some of the ones are used a lot. Cin, used by almost every C++ programmer to read data from the keyboard, does not check to see that it's going to fit in the buffer where you're going to put it. So you can use cin.get line, that will check. Similar problem is get string. It just reads characters until it's read all at once. It doesn't care if there's not enough space to put it. It just stores it in memory and overwrites whatever's there. Too bad. And there's also a whole bunch of scanf programs that do the same thing. Have to watch out for those. Old C functions like string copy, string concatenate, do not care if the buffer where they're putting it is big enough. It just overwrites it. There's string end copy. That's copies. In that version, you specify the length of the buffer, and it will not copy more than that. And similarly, there are several ones that have better versions. So use the safe versions. In fact, if you use the Microsoft Visual C++, it gives you a warning message if you use any of the potentially dangerous functions. Data expansion. Sometimes you're reading a character string, and then you go through and replace some characters, particularly if you're talking about URLs and things that are HTML encoded. If you have things HTML encoded, it might not ever include the greater than sign. Instead, it uses ampersand GT semicolon. And that will then get converted to a greater than. Well, you notice that ampersand GT semicolon is 4 characters greater than. So if you have something in HTML and you want to convert it to HTML encoding, and there are many functions to do HTML encoding, just say, take this and HTML encode it. Remember that the HTML encoded version may very well be much larger. If there are lots of brackets, then it can become much larger. So the output buffer has to be bigger than the input buffer, or it's not going to fit. And of course, remember, Unicode is 16 bits, ASCII is 8 bits, it's twice as big. If you go from ASCII to Unicode, buffer has to be at least twice as big. Now, there are several programming languages that avoid buffer overflow problems. Java, Python, C#, all check every array reference to make sure that you don't have a overflow. C++ and C are languages that don't, but Java, Python, and C# do not, or do check, I'm sorry, they check, C++ is not. Stack canaries. Now, stack canaries are used to see if the stack or a variable is overflowed. What it does, it's pretty simple. It puts this value after your variable. In fact, it puts them after every variable, usually more than one word, several words of the stack canary. The stack canaries can be random numbers that the compiler knows what the random number is, and then after you've modified cow, it checks, is the stack canary correct? Has it been changed? In the Microsoft Visual C++, the stack canary is binary CC. So they use each byte is CC. So you have 4 bytes of CC. That's the value that it puts in the stack canary. And then before the program returns, it goes and checks all the stack canaries. Are they still the same? Have they been changed? Are they still CC? If they are, everything's good. If they're not, it will stop your program and print an error message. That's what happened to my program when I ran it before, where I thought I could fool it and get a buffer overflow exploit. No, apparently the stack canaries were there. I thought there are options in C++ to say, don't put the stack canaries there. I thought I had done that, but apparently not. So, and then there's a feature in almost all the newer processors, Intel ARM, called data execution prevention. The program instructions are in one segment. I think I showed earlier, you have a segment for programs, a segment for constants, global data, and then a segment for the stack and a segment for the heap. You can specify in the pages, the pieces of memory that hold the program, that you may run program from this. In other words, when it goes out to do a instruction fetch, you can instruction fetch from certain parts of memory, but you may not do an instruction fetch from other parts of memory. Most importantly, you cannot do an instruction fetch from the stack. So if a user thinks they're clever and has managed to overwrite the stack with a code, when the program tries to jump into that program in the stack, the data execution prevention will not allow it to execute programs in the stack. You'll get a execution prevention interrupt, program will stop, print a nasty message. Now, the attacker will have been able to keep your program from running, be able to crash your program, but that is not as nasty as loading their program onto your server and executing whatever they wanted to. Might point out, you're a programmer, it's all about you. Computer security is your issue. If you write insecure programs, then you're the one that makes the users vulnerable. If users are running programs that are vulnerable to attack, it's the fault of the programmer. On the other hand, of course, if you write secure code, if you write programs that cannot be easily broken, then you are protecting your users from attack. Here's like a last poll question for today. Let's try this one. There's always a wise guy out there.
when the option should be dies if there's a change in memory.
Well, you can assume that some of these, like if it's detected, it will blow off your program. Yes, text. Usually, most systems do not detect silently. They are very vocal, and this is usually a fatal error if it gets a kind of error. All right, let's vote in. Okay. More answers here. And hey, okay, I didn't fool too many. There's always a wise guy who somebody said makes the program sing. No, it's primarily to detect something that allows the program to perform an overflow. No, it will detect that the user has stored data after a variable, in other words, in some memory. And when doing so, when it detects it, it will terminate the program with some nasty message and stop your program from executing to avoid the execution of some arbitrary program that might be loaded in the stack. Also, besides malicious, sometimes programs just don't work correctly, and you'll find out sooner rather than later. It's much better to have it tell you, oh, you've done something wrong, than to silently change a value in a program. As you look at the code, that variable is never changed, and yet it's suddenly changed by something else. It's very hard to find. Okay. Another thing that's done to help avoid these problems is that the systems put the stack at a different location every time you run the program. I mentioned the stack, it has some arbitrary address, where the stack starts at one address and then goes down, and the heap goes above. What is that address? Well, earlier, it always was a fixed address, always the same number. Now, it picks a random number and puts it, the advantage of this is that the values in the stack are in different numerical locations every time you run the program. So if you run it once, and somehow the user learns what the values are, if you run it again, it's someplace else. Okay. Chapter 31 of the textbook, or Appendix H, I think. The very end of the book, before the index, there's a list of programming or implementation rules. I went through those. There are a bunch of them. I found about 4 or 5 of them that I thought were particularly important. So let me just quickly go over these. Yeah, these are actually in the textbook, and you can look them up. Rule 31.4, check the error status of every function. Many functions return an error. Now, if you're in Java, if there's an error, usually it throws an exception. That's easy, you got to find it. But in C and some other languages, it just returns usually like a -1. So normally it returns the number of characters it read, but if there's an error, it returns -1 or something like that. Returns an error code. Always check the error code. Do not execute the function without checking the error code, because if there is an error and you don't check it, your program doesn't know there's an error, just keeps on happily going, and something's not working. Of course, as a programmer, it's always good to know when something doesn't work early. If you don't feel like burdening your production code, check the assert statement in Java and C++. Asserts, you can say assert and then give a logic of assert, 5 not equal to 0. 5 is greater than or equal to 1, or something like that, whatever you want to. And if asserts are being used, use an option to turn on asserts, then if that happens, it stops your program, prints out an error. And then when you run it for production, turn off that code. And a lot of languages, it doesn't generate any code, searches automatically don't do anything. Another sin that I've seen graduate students write programs with empty try catch block. You do a try, some code, catch, bracket, nothing. I saw a graduate student give me a program that got an error every time. But since you got the error, jumped to the catch block, which didn't do anything, and the program just kept on running like nothing had happened. And they thought the program ran just perfectly, turned it in. It never worked correctly. If they printed an error message in the catch block, they would have known. Don't let error checking go by without noticing it. Okay, pretty easy. Okay, another one, I think we mentioned this last time. If you have sensitive data in your program. When you're done with it, you don't just leave it in memory. Because when your program terminates, the value of memory is out there and somebody else has a program and they allocate the heap or the stack. The operating system doesn't clear anything. It just leaves the value. And so you can go out and look at the memory. Those of us who have hacked many years ago, one of the tricks was to do a malloc, acquire vast amounts of memory, and then scan through it looking for interesting values. See what you can find. That's some other program left. So whenever your program is done with sensitive data, whenever you're done using it, erase it, overwrite it. At the end of the program, overwrite anything of value. Because if you have something in memory, it might still be in memory and somebody else might see it. By the way, in Java, strings are immutable. You can't change a string. You cannot overwrite a string, which is why the password functions return an array of characters, which you can overwrite. Warnings, when you compile something, get a warning, don't ignore it. Typically, your program will run if you have warnings. It usually will not run if you have errors. You get a warning, but if you have a warning, that's the compiler's way of telling you something's not right. You probably ought to take a good close look at it. Now, sometimes it gets warnings and you go, yes, I know, I'm doing that on purpose. But typically, in a lot of places, they want programs that don't get warnings. And my last programming rule, check inputs for validity. That's what I think that's what I said today. Check to make sure they're the right type, check sure that the values are in range. And also, when you have a function or a method, when you're getting parameters, it's worth a little bit of code, maybe some assert statements, just to make sure those values are reasonable. Because it's so much easier to find out, oh, this value wasn't reasonable when I got it. Helps you a lot in debugging the program. If you just take the wrong value and use it later on, way down the line in the execution of the program, something goes wrong and you go, how did that happen? It's much easier if you caught it earlier. Okay. A couple of things I want to mention, a couple of announcements. Here is the schedule for the next couple of weeks. You will notice you are here, Buffer Overflow. We're doing cross-site scripting. A week from today is fall break. Take it off. Don't come to class. You got the day off. I said so. And then next week after that, we'll talk about SQL injection. I think I have some, hopefully I have some evil and cruel assignments for SQL injection. Also, I know what the paper is due. So is the undergraduate assignment. Undergraduate assignment, stay tuned. Okay, we'll talk about the dial service review. And then Wednesday, 2 weeks from now, is the second exam in the course. I'll grade that, give it back on the Monday, that is the 24th, Monday, October 24th. Give back everybody's grades. And the last day to drop is shortly after that, not that day. And by that time, though, you'll have 2 exams, you'll have homework assignments, paper, and you'll have a good idea of how the grade is in your course. And if you're one of the very few students who are doing poorly in the class, it would be time to take an exit and leave. Okay, now.
I have a question.
Go ahead. Yes, sir.
Are grad students allowed to drop classes if they're not doing good in them, or are they stuck for whatever?
Oh, yes, a graduate student may and should drop a class if you're not going to get. Remember, an F in a graduate class means you pretty much have lost it, because you have to maintain a 3.0 or better GPA as a graduate student. Unlike an undergraduate, if you get an F, you can then take the class again. Let's say you get an A. Let's say that's the only class you ever took, an F and an A, and it averages out to an A, a 4.0, because it just replaces that old class as an undergrad. That does not happen as a graduate student. Say you take one class and you get an F. You retake it, you get an A. It then averages the 0 and the 4, and you get a 2, which is a C. You have a long struggle to get up to a 3. If you get an F in a graduate class, that pretty much terminates your graduate program. So, very few of you have to worry about this. But I pointed out, of course, in some other class, if the instructor is evil and cruel, unlike old Dr. Williams, if they're evil and cruel, I'm going to flunk you. And I've flunked a bunch of them. You drop before it's too late. But don't worry, we'll have another exam. Okay. I did not get the overflow assignment written this afternoon. I had a really nice one that I liked. It just turned out to be a little bit too difficult. So to save you, because I am so nice, I decided to do an easier one. Basically, it's the program I was trying to run this morning. You have to run it successfully. It's very simple. Write a program that asks for a password. The correct password should be comp422. If you type in comp422, it should say, good job, nice password, and go on. But the program should be vulnerable to a buffer overflow so that there is some input that if you enter that, you'll still be able to log in correctly, even with the bad password. In addition to entering the program, either as a comment in Blackboard or send me a text file or something, tell me what input will cause your program to log in with data that does not appear in the program. Don't just say there's, reading the string, compare it to comp422 or compare it to this other answer. No, compare it to comp422 and then, now, if you are a graduate student taking comp620, then you're writing a paper. You do not have to do this assignment. You're going to want to write this program in C++ because it's very hard to do this in Java or Python. If you think that's a real problem, don't worry. I'll be giving you a template for a C++ program. You just write the code around it and they could do that. That you should see that on Blackboard today or tomorrow morning. It would have been today. It was almost written. But you were saved because the other more interesting, more difficult program turned out to be a real challenge it turned out to be more difficult than I wanted. So I finally took pity on you and came up with an easy one. Okay, that's enough for today. Any questions? All right. I'll see you on Wednesday and we will talk about whatever I said on the schedule, I'll talk about. It was a web threat. Okay.
Cross-site scripting.
Thank you. Yes, that's it. Good job, John. All right. All right. SQL injection next week. See you later. Bye.